Well, what a year it's been. We're finally on the last chapter, and this is relativity. I know it's not part of classical physics, but they did want to show you what happens to certain of the things that you learned earlier on when you take into account the things we learned since the time of Einstein. So Einstein's special theory of relativity is based upon two postulates. Number one is the relativity postulate. The laws of physics are the same for observers in all inertial reference frames. No one frame is preferred over the other. Okay? And number two is the speed of light postulate. The speed of light in vacuum has the same value c in all directions and in all inertial reference frames. Okay, now you can, a postulate is not the same as a law. It's a lot of things indicate that it's correct, but they have not been able to prove it. We can also phrase this postulate to say that there is in nature an ultimate speed, the speed of light, c, the same for all directions for all inertial reference frames. Light happens to travel at this ultimate speed. However, no entity that carries energy or information can exceed that limit. Moreover, no particle that has mass can actually reach speed c, no matter how much or for how long that particle is accelerated. Both postulates have been exhaustively tested and no exceptions have been found. So essentially what it does is it shows you that there's an asymptotic approach and speed in terms of the kinetic energy, right? Once you get beyond a certain level here, this is the area where relativity takes place, right? Okay, the dots show the measured values of the kinetic energy of an electron plotted against its measured speed. No matter how much energy is given to the electron, its speed will never exceed that or equal to that limiting speed of c. Okay? Now, the event is something that happens, and in every event can be assigned 3 spatial coordinates and 1 time coordinate. Among the different possible events are the turning on or off of a tiny light bulb, collision of 2 particles, the sweeping hand of a clock past a marker on the rim of a clock. Now, the key point here is that if 2 observers are in relative motion, they will not, in general, agree as to whether the 2 events are simultaneous. If one observer finds them to be simultaneous, the other generally will not. Simultaneity is not an absolute concept, but rather a relative one, depending upon the motion of the observer. If the relative light of the observers is much less than the speed of light, then the measured differences, the measured departures from similarity, are so small that they're not noticeable. Such is the case for all of our experiences in daily living. That's why relativity of similarity is unfamiliar. Only when we get to the spaceships and all the other things are these things going to occur. Okay? And it has the specific examples there. Now, figure OA shows the basics of the experiment Sally conducts while she and her equipment, a light source and a mirror and a clock, ride in a train moving with a constant velocity v relative to the station. The pulse of light leaves the light source B, okay, and travels vertically upward and is reflected vertically downward by the mirror, and then is detected back at the source, event 2. As in the example, if 2 successive events occur at the same place in an inertial reference frame, the time interval is measured on a single clock is called the proper time, delta t sub 0. Observers in frames moving relative to the frame, such as observers on the track watching Sally and her equipment, move will always measure a larger value, delta t, for the time interval on their clocks. This is known as the time dilation. Okay? So the time interval between two events depends on how far apart they occur in both time and space. That is, their spatial and temporal separations are entangled. So rather than just straight up and down right here, where you've got up, down, and a certain thing, if there's a movement involved there, okay, then it is going to involve a time dilation event. So, when two events occur at the same location in an inertial frame of reference, time interval between them measured in that time frame is called the proper time, or the time interval, or the proper time. Measurements of the same time interval at other inertial references are always greater. Okay, this shows the basics right here as well. And the relative speed for the two frames is v. Delta t, that's your time dilation, is delta t0. This is what is observed in this strict manner right here, divided by 1 minus the square of the speed versus divided by the speed of light squared. This v over c ratio is going to be known as beta. Okay, that's this is the Lorentz factor. Beta is the Lorentz factor. Okay, v, the speed, divided by the speed of light, is the Lorentz factor. Okay, and then this gamma right here is 1 over the square root of 1 minus this is called the speed parameter. So you've got your speed parameter, which is this right here, and you've got your Lorentz factor, which is this right here, right? The beta, the v over c squared. Okay? I'm sorry, the gamma, 1 over 1 minus beta squared. This is the Lorentz factor. This is the Lorentz factor right here. 1 over the square root of 1 minus beta squared. Beta itself is the speed parameter. Sorry about that. Okay, the mean lifetime of stationary muons is measured to be 2.2000 microseconds, right? The mean lifetime of high-speed muons is a burst of cosmic rays observed from Earth is measured to be 16.00 microseconds. To 5 significant figures. What is the speed parameter, beta, of these cosmic ray muons relative to the Earth? So essentially they're looking for the v over c value, aren't they? Okay. So the time dilation equation, delta t, gamma, delta t0, is the proper time interval. Gamma is 1, and this is the square root of 1 minus beta squared, where beta equals v over c. We obtain, first of all, this one right here, right? Okay, so the proper interval is relative to rest, specifically t equals 2.20, and we're told that this right here is 16 microseconds. Therefore, it's 1 minus this divided by this squared, okay? And it's the square root of all of this right here. And so that turns out to be your beta value is 0.99050, okay? 0.99050. This is your speed parameter beta, right? Speed parameter beta. Okay, now the next one, and this is one I really liked. Premise of the Planet of the Apes movies and the book is that hibernating astronauts traveling far into Earth's future to a time when human civilization has been replaced by the ape civilization. Considering only special relativity, determine how far into Earth's future the astronauts would travel if they slept for 120 years while traveling relative to Earth at a speed of 0.9990 times the speed of light. So they're pretty close to the speed of light. First outward to Earth and then back again. Okay? So 120 years. We solve the time dilation equation for the time elapsed as measured by Earth observers. That's your T0 right here. Okay, so this delta T right here, this is your 120 years that they themselves experience. And it's 1 minus, and then the factor is 0.9990. And both of these have C, and then C in the denominator cancels out, right? So it's thus 1 minus this, and this is squared. So this yields a delta T of 2,684 years that occurred on Earth while they were experiencing 120 years. But then they were going pretty close to the speed of light there, weren't they? Okay, the relativity of length. Okay, the length of an object measured from a rest frame of an object is its proper length or rest length. Okay, measurements of the length from any reference frame that is in relative motion parallel to the length is always less than the proper length. Okay, so if the relative speed between frames is v, the contracted length L and the proper length are related by this same Lorentz factor, right? So it's L, only here it's divided by this factor. Okay? You've got your beta parameter again there, which is your speed parameter, and your Lorentz factor again. So does the moving object really shrink? Reality is based on observations and measurements. If the results are always consistent, and if no error can be determined, then what is observed and measured is real. In that sense, the object really does shrink. However, a more precise statement is that the object is really measured to shrink. In other words, motion affects it. Okay? So if you want to measure the front to back length of a penguin while it's moving, you must mark the position on its front and back simultaneously, rather than at different times. And how to do that is not trivial. So, time dilation and length contraction as seen from such a frame. And this goes through the whole example there in your book, and it's good for you to go through that and look at how exactly this sort of things take place in terms of the length changes, okay? And remember, as long as things are in motion, it's going to be shrinking in size. And this continues on and shows you how the relationships are related and to what V value can actually be for these. So a rod lies parallel to the x-axis of reference, frame S, and moving along its axis at a speed of 0.630 times the speed of light, Its rest length is 1.70. What will be its measured length in frame S? So the length of the rod is measured in the frame in which it's moving. It's related to the rest length, L0, by this factor right here, right? Okay, and this is L0 divided by gamma, the Lorentz factor, where gamma is the Lorentz factor, right? 1 over the square root of 1 minus beta squared. And beta squared is the speed parameter, V over C. Since gamma must be greater than 1, L is less than L0. L0 is 1.7, beta is 0.630. So substituting them into this equation, you get this value right here. Instead of 1.70, it is 1.32 meters when the frame of reference is where beta equals 0.630. So the length of a spaceship is measured to be exactly half its rest length. To 3 significant figures, what is the speed parameter beta of the spaceship relative to the observer's frame? By what factor do the spaceship's clocks run slow relative to the clocks in the observer's frames? So we have a length one here, and we also have a time one here. And I'll go to the next video to go through that problem.